Hi everyone, welcome back. This is Earth and Space Science 102. I'm Stephanie Welch, and today we're going to talk about the moon. So we just came out of talking about the formation of the solar system. We did a little bit of an overview of all of the objects that are bound by the gravity of our sun, stuck in this in the solar system of ours. And we're going to talk about today our nearest celestial neighbor, our moon. Basically the object that makes our planet very unique, very different from all of the other terrestrial planets. We're the only planet to have a really large companion, a large neighbor like our moon. So we'll go on to talk about lunar phases today, the tidal locking phenomena with the moon, tidal friction created by tides. We'll talk about the moon missions, the manned moon missions in the Apollo years, and so on. So the theme today is just to talk about this one object. And later lectures we'll go on to talk about all the terrestrial planets, and you'll further see how the moon makes our planet a little bit different from those other terrestrial planets, and then the Jovian planets, and ultimately all of those sort of smaller miscellaneous objects in our solar system. So getting started talking about the moon is really not all that dissimilar from all of the other objects that you can see in the night sky, and occasionally even sometimes the daytime sky, making it different from a lot of those other nighttime objects. It rises in the east and sets in the west, just like stars do, just like planets do, just like the sun does. And that aspect of the moon is all about our moving and not necessarily the moon moving around. The tendency of all of these objects, stars and planets and our sun, to rise and fall and to rise in the east and set in the west is all about our rotation. As Earth rotates in the eastern direction, we have all of these objects continue to move up into the horizon and become visible to us. Now, the tendency of the moon to go through different phases and to rise and set at different times every day, that actually doesn't have anything to do with the Earth's rotation. That has to do with the motion of the moon itself. So the moon actually rises and sets a full 50 minutes slower, 50 minutes later every single day until it loops all the way back around again, and it's going to rise and fall at the same time. So the reason for that is because the moon is in orbit around our planet. It is bound by the gravity of our planet in the same way that we're stuck in orbit around the sun. And these two objects are almost, but not quite, in the exact same plane as one another. So the orbit of the moon is just slightly offset, just a little bit from the orbit of the Earth around the sun. And that's going to make things a little bit interesting a little bit later on when we talk about eclipses. So the moon rises a full 50 minutes later every single day, sets a full 50 minutes later every day. And so that means that some of the lunar phases are actually going to be visible during daytime hours, as we'll see. So as the moon orbits around Earth, it takes a full 29 and a half days to complete a single orbit. That makes for the potential of having 13 full moons in a year, or basically, sort of roughly speaking, it takes about a month for the moon to undergo a total orbit. It's a little bit less than a month. It doesn't perfectly match up with the orbit of the Earth around the sun, but that's at least where the origin of the word month comes from. It starts off with the word moon. So think of a month as sort of a month. You know, it's an origin from the word moon. At any given time during the moon's orbit around Earth, the moon is reflecting light from the sun, but only on the side of the moon that's facing the sun. So only half of the moon is reflecting light from the sun, and that's the part of the moon that we can see. So essentially, as the moon continues to orbit around Earth, we see different fractions of that illuminated surface, but we can only see up to half of the moon, and sometimes it's going to be that side of the moon that's facing towards us, making it look like the entire thing is lit up, but only at any given time is half of the moon lit up from the sun, or reflecting light from the sun. So as the moon undergoes a complete orbit around Earth, it starts from being in a position between the Earth and the sun to being completely on the other side and going all the way back around again. And again, a really good sort of easy way of remembering all of these orbits and all of the rotation of all of these individual objects is to think about everything happening in our solar system as being sort of part of one kind of continuous whole, and having all of these objects within our solar system rotate and orbit in the same direction, basically counterclockwise if you're looking at all of this from above the Earth's North Pole. So if you're kind of looking down at everything, imagine someone circling somebody, stirring a big pot and stirring it in a counterclockwise direction. So that's both the orbit of the moon around the Earth and the Earth around the sun. It's all happening in a counterclockwise direction as viewed from up above the Earth from the North Pole. So from this perspective, the moon undergoes a very, very slightly elliptical orbit around the Earth, sometimes getting a little bit closer, sometimes getting a little bit further away, but the proximity of the moon to the Earth doesn't affect the actual lunar phases. The position of the moon in orbit is the thing that's going to affect the lunar phases. So I've gone through and we've numbered all of these lunar phases from 1 to 8. And you have to think about this whole process as not having these lunar phases be sort of one of these 8 phases, but it being a constant grayscale. The moon is constantly either waxing towards full or waning away from full. And we just recognize these 8 individual stages just to make our lives a little bit easier so that we can have names for these individual phases. Names that you probably recognize like crescent and full and maybe even gibbous. These are all names that we attribute to some of these individual phases. So we'll go around the entire process and we're going to start with the position that has the moon strictly straight in between the Earth and the sun. From this perspective, we call this phase the new moon phase. If you think about it, the side of the moon that's going to be reflecting light from the sun is going to be the side of the moon that's facing away from Earth. And at the time when this phase is most visible, the sun is producing so much light that you can't see the moon in the sky, whether or not it's really lit up at this point. And it's not. So this is almost sort of like the absence of the moon in the sky. Even though it's still there, we have a really hard time seeing it because we're seeing that face of the moon that's constantly in shadow. So we're seeing the dark side of the moon, the side of the moon that's facing away from the sun, and we're seeing it directly overhead. It has the potential to pass directly in front of the sun at this point and produce what's called a solar eclipse, but that doesn't happen every month for reasons we'll talk about in just a minute. So that's the new moon phase, and when that phase has the moon directly overhead would be at noon every day, essentially the same time that the sun is directly overhead. So as you go a couple of days forward in the cycle, a few days forward, we get to the next phase, what's called a waxing crescent phase. This would have the moon being directly overhead at about 3 o'clock in the afternoon. So this is a phase that's probably the most visible during daytime hours. Has the moon being visible at about 3 o'clock in the afternoon, and it's just a tiny little sliver of light on the right-hand side of the moon. Later on, another crescent phase is going to have that sliver of light on the opposite side of the moon. It's going to be a waning phase instead of a waxing phase. So as we go forward another few days, the next phase that we're going to identify is called first quarter. This has the moon visible, the most visible and directly overhead at about 6 p.m. And this phase is going to have the right half side of the moon illuminated, at least from our perspective on Earth. And it's always about our perspective when we're talking about these phases. And the left side in shadow. As we continue to move forward, at about 9 p.m., the moon would be directly overhead. This is 9 p.m. a few days later again. And we call this the waxing gibbous phase. This is sort of like an inverse crescent. Instead of having just a sliver of light, you only have a sliver of the moon that's still in darkness, that's still not reflecting light from the sun. So essentially 3/4 of the face that is facing Earth at this time is going to be illuminated by the sun, and the other quarter is going to be not illuminated. So we see it as sort of an almost full moon. And that's why it's going to be most visible and directly overhead at about 9 p.m. Then finally, we've built up towards what we call full moon. This has the moon on the opposite side of the planet than when we started at new moon. So the entire illuminated half of the moon that's reflecting light from the sun is now facing Earth, and it rises at about 6 p.m., but it doesn't get to be directly overhead until right at about midnight. And so both for the reason because the moon is going to be reflecting light from the sun across its entire face, and it's visible throughout the entire nighttime cycle. This is when the moon is the most visible and the most beautiful. And so this is the most important of all of the lunar phases from a number of different perspectives. So as we then move away from full moon and back to new moon again, we're going to see all of the same phases, but almost sort of like the inverse of all of those phases. You're going to see the opposite side of the moon reflecting light from the sun, and the other side of the moon in shadow, in darkness. So as we go forward another few days, the next few days, we're going away from full moon and back towards a gibbous phase again. So this has, in this case, the left side of the moon illuminated and the right side of the moon in darkness. It's most visible at about 3 o'clock in the morning. It's directly overhead at about 3 o'clock in the morning, rising at about 9 p.m. and setting at about 9 a.m. As we go forward a few more days after that, we continue to sort of shave away the light from the right-hand side of the moon and replace it with darkness again. So a few days later, and this time at about 6 o'clock in the morning, you have your next phase that's going to be visible. This is called third quarter. And to get the origin of the name, you have to kind of think about the first quarter, the second quarter being the full moon, and the third quarter being this last stage. It's also in some cases called the last quarter, and maybe that makes a little bit more sense. This phase is most visible. It's directly overhead about 6 a.m., and it has the left face of the moon, the left half of the moon illuminated from the sun and visible, and the right half in darkness. And then finally, we have our last phase before we cycle back around again and begin new moon phase. A few days after that, you have your waning crescent. So all of these stages that follow the full moon are all waning stages. Everything that builds up towards the full moon are all waxing stages. So you probably remember wax on, wax off. Think about wax on, wane off for these lunar phases. So this 8th lunar phase happens a few days after that last quarter or third quarter, and it's going to have just that sliver on the left-hand side of the moon illuminated from the sun, reflecting light from the sun, and the rest of it in darkness. It's most visible at about maybe 9 a.m. It has the moon directly overhead at about 9 a.m. Then we can basically just sort of start over again. You're back at the new moon phase. All of these phases have much bigger implications than just looking up into the night sky and maybe naming all of these individual phases. The reason why I like to start with the phases is because we associate some of these phases with particular events, like certain types of tides, spring and neap tides, and certain events that might block the light from either the moon or the sun from reaching the Earth. These are called eclipses. So we'll start with the eclipses. A solar and or a lunar eclipse, no matter which one you're dealing with, is basically a case where either the moon or the Earth is blocking light from reaching the other object. Because you've got these objects in almost the exact same plane, it's going to be possible, at least during certain times, for all three of these objects to line up. And if they line up, it's possible for either the moon to block light from getting to the Earth or the Earth to block light from getting to the moon. So it's going to take a special set of events. We'll talk about what has to happen in order to make this possible. But remember from the first case that if these two objects had the exact same orbital plane, if they were all moving around in exactly the same dimension, then this would happen every month. It would happen every time you have a particular lunar phase. So when you have the lunar phase that we call a new moon phase, that's part of the conditions that you need for a solar eclipse to be possible. And solar eclipses are really, really cool. Whether you have a partial solar eclipse or a total solar eclipse, you're blocking light from the sun from reaching the planet Earth. And in the past, in ancestral astronomy and with the ancient peoples of Earth, they saw this as a terrible, terrible sign. And if you didn't know any better and you weren't warned that this event might be taking place and that the conditions were right for this, if suddenly the light from the sun went out right in the middle of the day unexpectedly, you'd probably freak out too, and you'd probably think that this was a really ill-fated omen. Now we can just recognize this as something that really, really cool and fairly unique that happens every once in a while. So in the case of the solar eclipse, pictured over here on the right, you're having some event that's blocking light from reaching the Earth, and that event is having the moon cross in between the sun and the Earth, blocking the light from reaching us and essentially casting a shadow on the planet. If you're at the exact perfect position on planet Earth, it's possible to see a total solar eclipse. But because the moon is far enough away from Earth, we don't have a complete blocking out of light from the sun. Instead, we have almost an entirely dark sun for that small period of time if you're on the right position on the planet Earth. A long time ago, when the moon used to be closer to Earth, it was probably possible for the moon to completely block out light from the sun. So even a few million years ago, even maybe halfway through the history of the Earth, it would have been possible for all of the light to be blocked out. Because the moon's a little bit further away from us now, only sort of most of the light is blocked out. If you're dealing with a partial eclipse, then you're dealing with a case where the path of the moon only takes it part way in front of the sun. And so it basically winds up, the solar eclipse, the partial solar eclipse that I've seen, looked basically just like the sun was a giant Popeye's biscuit with a bite taken out of it. It basically looked like the moon was crossing over just sort of one corner of it, basically creating that effect where you almost have something that looked like a crescent sun. It was pretty cool to see. So the solar eclipse is only possible during that one phase. That's the first thing that you have to remember about these eclipses, that they're only going to be associated with certain lunar phases. The phase has to be new moon for a solar eclipse to be possible. This is a really cool picture of a solar eclipse as viewed from space. And it gives you, again, sort of a little bit of an idea of what's making this possible to begin with. It's just the moon getting in the way from light reaching the planet, casting a shadow down onto the planet. And that shadow is only going to affect only a small swath of the surface of the Earth because the moon's a relatively small object. A lunar eclipse is going to influence a much bigger, larger portion of people because in this case, you're dealing with the Earth being the object that's blocking the light from reaching the moon, and the Earth is 4 times bigger than the moon. So it's just going to cast a much bigger shadow. It's going to completely envelop the moon. That shadow is going to completely envelop the moon, and it's going to be visible from most of the Earth's surface instead of just a small swath of the Earth's surface. So what you end up seeing instead of just complete blackness, which is what you almost sort of expect to see with a lunar eclipse, because this light is completely blocked from reaching the moon, you see a much darker version of the moon, but because some of the longer wavelengths of light can actually move around the surface of our planet and still reflect off the sun, what you end up seeing is a red moon, or what some people refer to as a blood moon. So a blood moon event is essentially the same thing as a lunar eclipse. It's a case where the Earth is getting in the way from light reaching the moon, and you're only seeing reflected off those longer wavelengths of light, making it look red in appearance. And so it's another just really cool event to get to see. It's also a little bit more common and a little bit more visible across a wider swath of the Earth's surface than the solar eclipses. Now, just as the moon, the lunar phase has to be in the new moon phase for a solar eclipse, it has to be in the full moon phase for a lunar eclipse. In order to have the moon in the right position on the opposite side of Earth, it has to be in that one particular phase. So only on the night of the full moon every month is it in any way possible to have one of these blood moon events. And only really every few years on top of that, because of the next set of criteria that has to take place. So not only do you have to have the moon in the right phase, the new moon phase for the solar eclipse and the full moon phase for the lunar eclipse, you also have to have these orbits line up perfectly. And they seldom do because the orbit of the moon around the Earth is inclined 5 degrees away from the orbit of the Earth around the sun. So if you kind of want to think about the orbit of the Earth around the sun as being something kind of like the flat tabletop maybe, or a flat surface of water, then you have to think about the moon as being just slightly offset from that, slightly tipped in comparison to that other plane. And so that would have the moon crossing above and below the plane of the orbit of the Earth around the sun as it continues every month. So that's going to change from day to day, but it's going to only line up just every once in a while, making it possible for an eclipse to occur. You have to have those points where the moon crosses that plane, dips in and out of that plane. You have to have those points be at the same time as those individual lunar phases. And so that's what makes it a relatively unique event, something that only happens every few years, or even longer than that for a solar eclipse. So the tipped orbit of the moon plus the lining up of those 2 points where those planes intersect is what actually allows for an eclipse to occur. So we call the points where those 2 planes intersect the node. So if you think about maybe my 2 hands here as starting off in the same plane, but then maybe I just tilt one hand a little bit, that point where they intersect is the node. That's what you're looking for when you're trying to track the potential for eclipses to occur in the future. You need those nodes, those points where the 2 orbits intersect to coincide with either the lunar or the solar phase, only the new moon or the full moon phase. And then the new moon would allow you to have a solar eclipse. The full moon would allow you to have a lunar eclipse. It doesn't often happen during the exact same month, but it's at least possible. It's also possible once those orbits line up, once those nodes line up perfectly, to have a few eclipses take place over a short period of time. So we have sort of somewhat predictable eclipse seasons when you look at all of this geometry and figure out exactly when this is going to happen. There are going to just be times when it's a little bit more likely for these things to happen. Okay, so only a small part of the Earth's surface in the event of a solar eclipse is going to experience a full eclipse. Or in another way of thinking about this is that the path of totality is going to be relatively small. The path that is going to actually experience a total solar eclipse. In the case of a lunar eclipse, it's going to be a much bigger part of the Earth's surface. At no point is it going to be possible for the entire surface of the Earth and all of the people on planet Earth to actually see a lunar eclipse, because it's going to coincide with a particular time, making it impossible for people on the opposite side of the world, and let's say the Eastern Hemisphere, to visualize, to see an eclipse that might be visible for us. But at least from north to south, a really big swath of the Earth's surface is going to see it in the event of a lunar eclipse. In the event of a solar eclipse, it's a little bit more tricky. You really have to be on this perfect path. And the closer you are to the equator, the more you have to be directly on the path to be able to see the eclipse in totality. So I wanted to show you all of the solar eclipses that have happened for the last 16 years and will happen for the next 8 or 9 years to come. All of the total solar eclipse paths from the year 2001 to 2025. Some eclipses aren't actually going to be in totality for anyone. There was an eclipse that happened just a couple of years ago that doesn't show up on this map at all because it was only ever a partial eclipse. for us and for the rest of the northern hemisphere. In terms of the next total solar eclipse, the next one that's going to be visible for anyone in the United States is going to be a little bit later on after the year where this is filmed, on August 21st, 2017. On that date, on August 21st, 2017, there will be a total solar eclipse that carves this path in blue from the northwest of the United States down to the southeast. And so it's going to pass through Kentucky, Tennessee, down into Georgia, but it's not going to pass across where we are. Essentially, the perfect geometry that gets set up between having the sun, the moon, and the earth all in a nice little line is going to allow that shadow to get carved across that line of totality as the earth rotates through this eclipse event. So the point where this is going to be visible right at about noon is that little black mark, that little speck on the picture. That's going to be the point where this is the visible for the longest period of time. It's probably going to affect areas in western Kentucky for the longest period of time. The next one after that isn't going to happen until the year 2024, April 8th, 2024. And you can see the path of totality along that line. As you get closer and closer to the poles, you can see how all of these lines of totality become a lot fatter. They become a lot wider because you have to think about that shadow is spreading out across a wider swath of the Earth's surface simply because the Earth is going to be more tilted, essentially, and that line is going to be more tilted. The light's going to be more tilted as you get closer and closer and closer to the poles. It's also going to affect a fewer number of people. For instance, there aren't going to be a whole lot of people that are actually going to be able to witness the 2021 December 4th total solar eclipse because it's only really going to be visible across Antarctica for the most part. So that's eclipses. And when you really kind of just boil it down and get down to the nitty-gritty, the basics of it, it really, again, just has to do with those two things. Having the moon in the right lunar phase, either in new moon for the solar eclipse and full moon for the lunar eclipse, and having those nodes line up with those lunar phases. As long as those criteria are met, an eclipse is going to happen, but they don't happen very often, which is why these eclipse events are rare and not a monthly occurrence that we would get used to. It becomes special because of its rarity. The next thing that we're going to talk about that is also going to be related, at least in part, to the lunar phases are going to be the tidal cycles. So we're going to talk both in terms of daily tidal cycles. Those are really sort of straightforward, fairly easy to understand. And we're going to look at entire monthly tidal cycles. And it all has to do with the presence of the moon in orbit around Earth and the position of the moon in orbit around Earth. Now, first off, in terms of our daily tidal cycles, this is pretty easy to figure out. The moon is a relatively large object that's located pretty close to Earth, much closer than any of the other objects are out in the solar system, much closer than Venus or Mars or the Sun. And so being a large object in space and located fairly close to us, the moon is going to exert a gravitational pull on our planet in the same way that the Earth is exerting a gravitational pull on the moon. We both sort of, in a sense, sort of pull on each other. That's the universal law of gravitation. Two objects with mass are going to both be pulling on each other, and the force of gravity is going to be equivalent to the mass of those objects and the distance between them. Having the moon be fairly close means a larger force due to gravity. Now, because of the relationship between the Earth and the moon, we don't have enough of a gravitational pull to be able to actually create heat within the Earth and to displace the solid interior of the Earth itself. Maybe at some point in the distant past when the moon was much closer to the planet that would have been possible. But now with the current position of the moon, the only thing that's actually going to be manipulated and moved by the presence of the moon is going to be water on the surface of the planet. So the moon is going to create tides because the moon is pulling harder on one side of the planet Earth. It's essentially pulling in that one direction and displacing the water on Earth into something that's called the tidal ellipse or the tidal bulge. Now, it would be very easy at this point to get this mental picture of all of the water on Earth piling up on one side of the planet, that side of the planet that's closest to the moon. But because the Earth is constantly rotating through this, it creates a centripetal force, and it creates basically the water on Earth being in this ellipsoid shape, whereas the Earth itself is a little bit more spherical, more rounded. It basically creates sort of two peaks, one on opposite side of the planet Earth, both in line with the position of the moon. And that's where you get this ellipse shape from. So not only does the Earth's rotation influence the shape of the ellipse, it also influences how many tidal cycles you would get in a given day, and the idea of going into low and into high tide. As we continue to rotate through this ellipse, and in this picture here, you're actually looking down onto the Earth's North Pole. You rotate through this ellipse, and the water on Earth gets to be a little bit lower in elevation during the kind of skinnier part of this ellipse. That's low tide. And as you continue to rotate a few hours later, maybe 6 hours later, you're on the high part of this ellipse. And the water on Earth is going to be a lot higher in elevation. That's high tide. And so whenever you have people trying to do, to take measurements of sea level, trying to figure out what eustatic sea level actually looks like, global sea level, global average sea level looks like, they have to first take away the influence of the tides, because the tides are this constant daily natural fluctuation in the elevation of sea level. When you look at this from the perspective of individual locations on the surface of our planet, because Earth is not a perfect sphere, and because the water doesn't cover the entirety of our planet, the influence that tides play in the shape of coastlines and so on is going to be just as much influenced by the shape of the basin and the size of all of these individual basins of water as it is to this tidal cycle and to the presence of the moon. For instance, in the Gulf of Mexico, we have much, much smaller tides, a much smaller overall variation between high tide and low tide, and a completely different frequency of how many high tides and how many low tides you get in a given day than you get in the Atlantic or in the Pacific. Typically, in bigger basins, you have a larger discrepancy between high tide and low tide. Okay, so that's kind of going into tides in general and just having high tides and low tides all taking place in a given day. It's also possible, as the moon continues to orbit around Earth, for this overall discrepancy between high tide and low tide to become even bigger or smaller. So the magnitude of tides, you could say, is going to be dependent, at least in part, on lunar phase. So the position of the moon in orbit, and this is something that's going to vary throughout an entire month as opposed to just varying from throughout a day. So the lunar phase is going to tie into these tides by having these things called spring tides and neap tides. Essentially, what's at play here is that the moon is not the only object that's fairly close to the surface of our planet and exerting a large gravitational pull on our planet. It happens to be the closest, but it's not in any respect the most massive. The sun is much further away from us than the moon, but it's many, many, many times more massive than the moon is. 99.9% of the mass of our entire solar system, in fact. So because it's so much more massive, it's actually possible for the sun to manipulate tides just as the moon manipulates tides. So it's a little bit of a trade-off of having the moon be a little bit closer to the Earth versus being less massive. Those things basically work to create an effect of having the same sort of tides be the fault of the moon as the fault of the sun. So a spring tide is going to be something that happens when both the sun and the moon are both, in a sense, working in tandem to displace the water on Earth. When you have either a new moon phase or, as it turns out, a full moon phase, then you're taking the water on Earth, and both of those things are pulling on Earth's water both in the same direction. The sun, let's say if you're dealing with the new moon phase, the sun might be pulling on Earth's water in the one direction, and the moon is basically, from our perspective, located in that same direction. So the moon is going to be pulling in that same direction. The tidal ellipse is going to occur because of the Earth's rotation. It's going to create that effect of the tidal ellipse and the tidal bulge. And this is going to have that ellipse occur in the same direction, both because of the influence of the moon and the influence of the sun. So what this really means is that you have a bigger ellipse, a bigger ellipsoid shape, less circular shape than you would at other tides. You have a bigger discrepancy between the elevation of sea level at high tide and the elevation of sea level at low tide. And so these are called spring tides, not because this has anything to do with the season of spring, but because these tidal phases are when springs that empty out into the ocean are going to become visible, when sea level is actually low enough for those springs to be revealed. Now, the next type of influence between these tides and the lunar phases is going to essentially be the opposite of spring tide phase. The spring tide is either going to be the new or the full moon phase. Basically, both of those are going to have the moon exist in the same line with the sun. If you get the exact opposite of that, it's called a neap tide. Either in the first or third quarter, in either one of those positions, the moon is essentially pulling on Earth's water in one direction, and the sun is pulling on Earth's water in the opposite direction, 90 degrees away from that direction. So it's almost like instead of the two working together, that's when the two are trying to pull on Earth's water both in opposite directions, and they almost completely offset each other. So that's when tidal forces are going to be weakest, when you have either the first or third quarter phase. So the ellipse shape is going to be the most diminished overall. It's going to be the smallest overall. You're going to have something that almost looks like a tidal circle, a tidal sphere, instead of a tidal ellipse. And so this means a smaller discrepancy between high tide and low tide, a smaller overall variation. Now, this constant push and pull of water on Earth is more than just something that's going to affect us locally, affect us when you have people that are fairly close to sea level. It's actually going to do something between the relationship between the Earth and the moon. The effect of tides actually works as an external factor that can influence the Earth's rotation, the moon's rotation, and the orbit of the moon. All of these things end up getting affected by the force of tides. So tidal friction essentially works in the same way as friction does on the surface of our planet. Friction works between your car and the road to slow you down over time as you take your foot off the accelerator. Tidal friction does the same thing to the rotation and the orbits of all of these individual objects. Tidal friction, the effect of tides influencing both the Earth and the moon, has actually thought to slow us down over time. Our rotational cycle, our total amount of time that it takes for Earth to complete one rotation, is thought to be substantially slower than it would be if the moon weren't there at all. So if the moon weren't there at all, we might have 15 or 16-hour days, much, much quicker overall days than we do now, where we have 24-hour days. So we would have much quicker days. The rotation of the moon would be quite different if it weren't for this tidal force. And the distance between the moon and the Earth is also affected by this tidal friction. The work of tidal friction actually works to take the moon and move it a little bit further away from Earth every day and every year. It's very, very minute, and it's a very slow process, but the moon is actually leaving us. The moon is orbiting a little bit further away, a little bit further away, and a little bit further away with every single passing year. We think that it could have been as much as 50 or 60% bigger in the sky as even just 500 million years ago. So we think over time that the moon is orbiting further and further and further away from our planets. This both diminishes the effect that tides have on our planet. So we think tides were actually bigger in the past, and we think that the moon was actually bigger in the night sky. Big enough that in the past it was probably possible to see an actual total solar eclipse where the moon completely blocks out light from the sun, as opposed to what we have now where just most of the light is blocked out. So tidal friction accomplishes a lot of individual things. One of the probably coolest things that it does is to lock the rotation of the moon to facing the Earth at all times. It creates this effect of tidal locking, and it's not really the only object that does this. Whenever you have planets that are orbiting too close to their star, it's actually possible for this to occur with those planets as well. The planets become what we call tidally locked. So if an object is tidally locked, it means that it's always constantly sort of pulled back so that it's facing the planet at all times. So imagine the moon as an actual object with a face and a nose. And it's helpful to think about it in this way because in this little image that I have that's going to be associated with the slide on tidal friction, you have the moon with this one big giant mountain peak that it actually doesn't have. But the textbook illustrators created this big peak on the moon just to have one sort of representative feature. And think about that big peak on the moon as being sort of like a nose on the moon. Imagine the moon is actually facing Earth at any given time. For it to be tidally locked, that doesn't mean that the moon doesn't rotate at all. It's constantly rotating, but it only rotates once during an entire orbital cycle. So it takes 29 and a half days for the moon to complete one orbit and to complete one full rotation. It does this by taking that same face of the moon, and that face is sort of visible with that big nose in that picture, and it's constantly doing a quarter turn with every quarter orbit to keep that same face facing Earth at all times. So the expression "the dark side of the moon" is one of these expressions that I really love. And when you stop and really, when you understand something about the moon and you stop and really think about that expression, it becomes a lot more abstract than you really want to think it is. The moon is constantly rotating, so there is no consistent dark side of the moon in terms of the moon reflecting sunlight at any given time. There is, however, a side of the moon that's always facing away from our planet, that's always facing in the opposite direction of our planet. Sometimes during new moon phase, it's illuminated. Sometimes during, let's say, full moon phase, it's not illuminated. So it's not necessarily dark, but it's definitely the abstract side of the moon and the side of the moon that is not facing us. Another way of thinking about the moon is that the moon has worked probably many, many times in the Earth's past as a shield for our planet, because having this object about a quarter the size of our planet in place has probably blocked some big impacts from actually hitting Earth. When we were actually able to visualize that opposite side of the moon, when missions like the Lunar Prospector were able to take pictures of that opposite side of the moon, we found it to be much more heavily cratered than the side of the moon that's actually facing the Earth. So you can kind of think about that opposite side of the moon facing away from Earth at any given time as bearing the brunt of some of the impacts that otherwise might have hit Earth and may have had major implications for the stability of life on Earth. So in many, many ways, not having the moon would drastically change conditions on Earth and possibly even make it so that life on Earth was not possible. The last thing that I want to talk about in terms of the moon specifically, eventually I'll get into talking about the Apollo missions that were to the moon, but the last thing that I want to talk about in terms of the moon is the origin theories, or one really sort of origin theory on how the moon got to be in orbit around Earth. Now, the first thing that I want to talk about is the necessity for coming up with some kind of an origin theory. It's very easy to think that just because we have a moon, it's probably not that unique, that maybe all planets that are like Earth have a moon. But when you actually try to apply that to other planets that are similar to Earth in our own solar system, to the other terrestrial planets, it turns out that we're the only planet to have a large moon. Mercury, Venus, and Mars all are extremely, all have either no moon or have very, very small moons compared to the size of their planet. So effectively, Mercury and Venus have no moons at all. Mars has two teeny tiny little moons called Phobos and Deimos that wouldn't even be visible on the surface of the planet. They're basically captured asteroids. Our moon is a quarter the size of our planet, but only 1%, 1/100th of our planet's mass. So trying to come up with some explanation of how it got there and how that works in conjunction with the nebular theory of solar system formation is sort of a unique problem. And one of the main missions of the Apollo missions, one of the main objectives of the Apollo missions. So particularly the opposite side of the moon that we were talking about, that's so heavily cratered, gives us at least sort of one way of thinking about how the moon might have formed. Some of the earliest theories on how the moon formed in conjunction with scientific thinking and the nebular theory had the moon sort of breaking off from Earth as it formed. The math doesn't really work out. It doesn't really make a whole lot of sense, but maybe the moon actually was part of Earth to begin with. Maybe it was a captured object, meaning this object formed on its own and moved a little bit too close to Earth. But the physics of all of this and the math of all of this doesn't quite work out. Something the size of our moon probably had to have formed from the mother of all impact events. So we think that at some point during the first 500 million years of Earth history, at some point we actually didn't have a moon. We had instead a fifth terrestrial planet in our solar system, a fifth sort of rogue planet in between the orbits of Earth and Mars. And the problem with objects that exist a little too close to other big objects in the solar system is that inevitably, after millions and millions of years have passed, those two objects are going to get in each other's way. And there's going to be a big problem when those objects do get in each other's way. So when this sort of young kind of proto-Earth got a little bit too close to this neighboring object that was probably about the size of Mars today, about half the size of Earth and maybe a tenth of its mass, these two objects would have collided. And if they collided at just the right trajectory, a really low-angle trajectory, then the math would suggest that that impact would allow some of the Earth's mantle and some of the mantle off of this impacting object to be blasted back out into outer space. And that mantle material, this fairly low-density rocky material, could have coalesced in orbit to form our moon. It could have reformed. It could have allowed for accretion, for collisions between particles that reformed a new object, an object that has similar characteristics to our moon, 1% of the mass of our planet and a quarter of its size. So the moon may have actually been mantle from Earth and mantle from this impacting object. If it worked out just perfectly, if those two objects did in fact impact each other, run into each other in space, and if they did so at a really, really low angle, then the result would have been one large, big, lucky moon in orbit around Earth. So I've got a really, really cool simulation of how we think that this impact took place. And you can see first off that that impact was really, really low angle. Too high an angle, and you basically have the Earth growing in size but not acquiring a companion. If it happens just right, if that orbit, if that impact happens at a really, really low angle, that's the most successful at blasting material off the surface of the planet and allowing that material to come back and coalesce in orbit. And now you can see that that's exactly what's happening. There might have even been a second impact before this material eventually was allowed to actually coalesce back together and form a moon. The other result of this big impact event would have been that our planet grew as a result. Possibly the reason why Earth is the largest of the terrestrial planets may have had just as much to do with this impact event as the formation of the moon does. So it's a really cool simulation. It's a really, really cool idea. A giant impact as how our moon actually formed and how we ended up with this object that's now forever and ever and ever stuck in orbit around Earth. So it's really, really a beautiful theory because it allows us to explain how the moon originated where it did, how it formed where it did, but it's not so evolutionary that every single terrestrial planet should have ended up with one too. It is just as important to be able to apply a big theory like the nebular theory and allow for the formation of unique individual things like Venus rotating backwards or our planet acquiring a big moon as it is to explain how things are similar, how all the terrestrial planets are similar and how all the Jovian planets are similar. So it's a really beautiful idea, and we think it's the most, probably the most accurate, probably the most reliable model for how our moon formed. Certainly the one that makes the most sense. The last thing that I want to briefly talk about here is the history of our explorations of the moon and the history of the NASA missions. Of course, this originated with NASA itself, with the origin of NASA in the 1950s. And it's going to have started with the Mercury and the Gemini missions that figured out how to put a man in space, how to put a manned mission in space in orbit around Earth, eventually in orbit around the moon. But on July 20th, 1969, the NASA missions actually accomplished the main goal, which was to put a person on the moon, to put a human being, and eventually many human beings over the course of the Apollo missions on the moon. So the first person to walk on the moon was actually Neil Armstrong. And this final picture that I'll show you here has Neil Armstrong on the moon with his famous phrase, "That's one small step for man, one giant leap for mankind." So that's going to wrap it up for today with this whole lecture on the moon. In the next lecture, we'll talk about the terrestrial planets. And you have to remember that the moon is one of those things that's going to make the Earth unique in comparison with the rest of the terrestrial planets. And then we'll go on to talk about other objects in the solar system from there. Until next time, keep looking up.